It's 4:01. We'll be starting in a minute. So very, very warm welcome and good evening to every single one of you who has joined us today. And of course, to Dr. Martin, who has taken the time on from a different time zone to be with us. Thank you so much, Dr. Martin. And, it's we are all looking forward to learning a lot from this session. We really appreciate this aspect of you coming together and bringing so much of knowledge to us. So my name is Vijeta Shastri, part of the TIE Bangalore team. I would also like to thank Mouse Electronics team, our charter members as well, Saswati and Avinash, for coming together, setting up this, and looking forward to this beautiful session. So Dr. Martin, of course, is from Littelfuse, is a global principal. And today's topic is about power electronics to boost the commercial vehicle value chain. And what we would like to do here is that we'll start the session. It is being recorded as well. And Dr. Martin very graciously has promised to give us something that we can share with all of you who have registered and who are joining us so that you'll know more about this wonderful topic. And Dr. Martin will have a presentation and he will, of course, take the questions that come into the chat. The request that we have is during the presentation, as a very basic housekeeping rule, please stay off the audio video and also make sure that only very, very permanent and pertinent aspects are shared onto the chat. Okay. So with this, it's over to you, Dr. Martin. We are all looking forward to the session and thank you so much for taking time out once again. Looking forward, sir.
Thanks for the nice words. So on behalf of Mauser and Littelfuse, welcome to this session for today. And my name has been mentioned. I'm Dr. Martin Schulz. I'm with Littelfuse since about a year. I started here in February 21. Before that, I collected about 20 years of experience in power electronics. I did my PhD in power electronics and electrical drives. I'm a senior IEEE member, and some of my ideas even made it to patents. So today's session is about the long value chain that includes the commercial vehicle. So starting from the heavy-duty vehicle, the commercial vehicle is primarily bus and trucks. The question is how the energy is stored. It may be a battery electric vehicle, but there's a lot of development also going on in fuel cell electric vehicle. Besides the on-road sector, there's the off-road sector dominated by agricultural and tooling machines and construction machines. And in construction is supported by material handling, like forklifts, for example. Whatever you do in the commercial vehicle sector, the energy has to get into the vehicle, which means high-powered charging is part of the infrastructure as well. And if it comes to real high-power charging, and we're talking about megawatts actually, battery buffering may be a very nice option to relieve the grid of peak loads. Energy could be stored in hydrogen and be reused in hydrogen fuel cells. Then the hydrogen has to come from somewhere. So hydrogen generation and electrolysis may be part of the chain as well. And of course, on top of the chain, there is energy production. And if we want to get to a cleaner, environmental friendly transportation, we need to consider renewable energy, particularly wind and solar power. Then again, the vehicles may get smaller and get charged. So local chargers, be it AC chargers like wall boxes or DC infrastructure, is mandatory to also help with the last mile delivery vehicle. Last mile delivery vehicle in this case is low speed vehicles. You will also see last mile delivery vehicles in the regime 2.8 to 3.5 tons. But one of the more interesting markets as well includes the 2 and 3 wheelers. Then public charging might also be an option. And the gap that is still open is the passenger car. Passenger cars might become commercial vehicles, for example, those used as taxis. But as they have a second life as a passenger car in private hands, they're not really considered commercial, even if it's used for a commercial purpose. So what does the all-electric commercial vehicle look like? And please forgive me that I remain with the big thing. So a large-scale electric vehicle, like an electric truck, deserves or demands to have low-voltage MOSFETs, pressure sensors, temperature sensing, just to protect the battery. So the battery management system and the battery itself are the most precious parts in here. And monitoring is important, but also emergency handling is important. So emergency high voltage battery disconnect switches and technologies are needed. And in case of an accident, you also want the low voltage system to be safely disabled. So here, even low voltage battery disconnect switches come in. The more electric, or by now all electric vehicle has MOSFETs in all the low voltage supply systems and functions of the onboard electronics, be it a heated steering wheel or the onboard air conditioning system. Electric window lifters and wipers, they all run on low power and are controlled on low voltage MOSFETs. To protect those, electronic fuses and sensors for advanced diagnostics drop in. So here too, power electronics starts to replace classical fuses in the future. As the high voltage battery easily goes to 1000 volt by now, high voltage MOSFETs in 1200 and 1700 volts accompanied by IGBTs and diodes are necessary, partially for the onboard supply to convert DC of the high voltage battery to DC for the low voltage system, and as well in high voltage systems for the drivetrain. So the main inverters are today mostly equipped with IGBTs, but there is a tendency to replace those on silicon carbide MOSFETs in the future. We'll see where the trend ends up. So then, how to charge your electric vehicle, how to get the electricity into it. And to get you an insight into what charging commercial vehicle means, we're talking about output voltage and output current. And up to 900 volt today, with a maximum current up to 500 amp, you find the area for passenger car charging. So this is considered high power charging for passenger cars. Tops out at 920 volts and 500 amps, but is limited in power to 350 kilowatts. How does this compare to commercial vehicles? Well, the arrows lets you guess what happens. The standards already include voltages up to 1500 volt cutoff for the battery and allow currents up to a 3000 amp regime. This is high power charging for commercial vehicles, currently limited by 1500 volts maximum voltage and 3000 amp maximum current. The missing corner is a contribution to the maximum power outlet of 2.2 megawatts. But charging a vehicle 2.2 megawatts demands proper power electronics. And here is the small square. This one is the low-speed delivery vehicle for the last mile. The classical two-wheelers and three-wheelers charging at levels less than 100 amp and less than 100 volt, maxing out at something like 10 kilowatts only. There is something that you can consider a classical approach to build those high power chargers. You have a three-phase supply, typically 400 volt, which is given to an input stage for rectification. In this power regime, typically power factor correction is a must-have. And you get a DC voltage that is then again transferred into a high frequency AC. This high frequency AC is used to drive a galvanic isolation. So typically transformer in LLC configuration. And you get a high frequency output from it, which needs rectification to support the DC voltage of the battery. All of this is packed into one subsystem or charger module. And then the energy coming from the grid is handled by a multitude of those modules. So they get stacked to increase the output power to provide power to high power batteries. Single units today are constructed to support something like 60, potentially 100 kilowatts from a three-phase output, which already is a lot. And stacking is done to upgrade the power level on the one hand, potentially, depending on the control structure, also to achieve redundancy. So in case a single subsystem fails, it's not the whole charger failing, but it's only a fraction of the power use. On the downside, you have a lot of interconnection effort to do. So commissioning those systems and maintaining the systems is more stressful. And each of the system contains an isolating unit, which may not be necessary. So let's take a look into the solutions for that feature galvanic isolations. There's always a three-phase grid because from a single phase, you're not going to get those hundreds of kilowatts. There's an input rectifier. In this stage, it's just a different drawing of a Vienna Rectifier. And this one provides power to a DC link that in turn provides the AC to drive a series connected or parallel connected LLC stage. And then the battery is driven with up to 250, up to 750 volts, which is one of the limitations in this setup. A three-phase input with a Vienna rectifier is one solution. It became a widely spread one because it offers power factor correcting strategies, as well as limited control over the DC voltage. So the DC link voltage can be controlled to be higher than the rectified one, which at least gives you some control. Galvanic isolation stages are very typically LLC stages because those provide the highest efficiency, and efficiency really matters in infrastructure systems. Power output of each unit tends to be in the 60 kilowatt, potentially even 100 kilowatt unit. And depending on the components in use, efficiency can grow up to reportedly 97 to 98%, particularly with a high content on wide bandgap materials like silicon carbide. The challenge is to support the full CCS standard. CCS is combined charging standard, which allows 200 to 920 volts being charged. With the LLC stage, due to the frequency limitations, there is typically a factor of 3 involved. So 250 to 750 volts is reasonable. If you get down to 200, then you may be limited to 600 volt, while the standard would like to see 920. That's something that needs to be considered. So how about setting up this with non-isolated discrete components, which is something that is typically done a lot around the world. So this is a picture I took on a fair from such a setup. The setup consists of 2 parts that are sandwiched together. So this is the lower part of the sandwich, and this is the upper one. Imagine it's put together so that the fans on top of the picture match the heat sinks on the top of the left and the right picture. The input stage is Vienna rectifier. The output stage, and you can see the transformers on the right side of the picture in the center, is the series connected LLC. And now the trouble begins. This is 48 discrete components on 15 different heat sinks. From manufacturing point of view, particularly if you strive for automated manufacturing, that's a hazard. It features forced air cooling, and forced air cooling in this way brings 2 disadvantages. The one, well, you need fans, and the other is the airstream goes through the power electronic section. So it's not only covering the heatsink, it's covering all the power electronics. And that means dust piles up over time. Dust piling up or dirt piling up in power electronics degrades the thermal performance, which leads to degrading performance of the drive itself. In turn, regular maintenance happens. And if you think that's made up, here is a picture of a stack of 50 kilowatt units. I took this picture in Shenzhen in the vicinity of Hong Kong. And this particular stack is located in what they call a clean room. So this is a showroom with air-conditioned filtered air. And still, every 2 weeks, someone needs to get in and clean it up. So the better solution would be to put all the devices on a single heatsink and get air through the heatsink only, not making a mess in the power electronics by piling dust up. So how to build this on using isolated devices? Because that's the trick. You need isolated devices to set it up. And if you get for the very typical approach with the Vienna rectifier, the LLC stage charging the battery, then there's a lot of products that feature isolated backsides or top sides. This is the Isobus family members, and a single switch is available in typical TO package, but also in the SMPD for higher power ratings. If that's not high enough, go for mini blocks in TO227 to increase power levels. If half bridges are desired, then here too, there is modules or ready-made discrete components to carry half bridges. And also the rectification stage can be obtained in a single package. And again, if the power levels aren't sufficient, have half a half bridge with twice the power in the same package. So this is the way that discrete components with isolated backsides can be used. And they can all be mounted on one single heatsink because the backside isn't electrically active. And that's a big step ahead in thermal management and also in compactness of building it, which leads to higher power density or the smaller device with the same output power. Charging solutions today for heavy-duty vehicles, and particularly for fleets of vehicles, can be separated in 4 groups that get introduced now. This is a picture taken in the Netherlands, and the company Ibusco is quite prominent there. But what they do here is called depot charging. So the buses have plannable idle times and downtimes, or not downtimes, idle times. 50 to 60 kilowatts per charging unit are by far good enough because one charging station serves one vehicle at a time, but the charging time available is the night shift, something like maybe 4 to 6 hours. And 60 kilowatts, 6 hours, easily refills 300 kilowatt batteries overnight. For fleet operation, in delivery, be it people or goods, doesn't really matter, is a very nice option for fleet operation. It deserves another side note. Having a depot and the area allows for further services. You could use the vehicle's individual batteries to do balancing. You could charge several vehicles in a grid-friendly manner by exchanging battery power from one vehicle to another. So grid-friendly scheduling may also be an option. In case the grid demands support, if the chargers are built bidirectionally, then even grid support could be scheduled during peak hours. And peak balancing energy is expensive. So charging batteries at low rates and then offer grid supports at high rates would also make another business case. How big this business case could be? Well, here's a fact to think about. We all love Hollywood blockbusters, and we all know those yellow buses transporting pupils and students. Actually, the US has roughly 500,000 of those buses running in the US. But the US also features a 100-day summer vacation. 100 days a year, those buses do nothing but idle. If each of those can offer 250 kilowatts of battery storage, we're talking about 120,000 megawatt hours of highly decentralized battery capacity, available exactly in summer to support the grid when all those air conditions are operating. So yes, that's a pretty big thing for fleet operation, particularly for fleets as big as school buses. And I learned that India has a few millions of buses running, not only school buses, but also factories that pick up their employees and bring them to the workspace. And here too, that's a shift in the morning and a shift in the evening. The rest of the time, the bus is an idle battery. And why not use a battery for grid services and now and then pick up some people? And if you think that's a brilliantly new idea, think twice. This is a picture taken more than 100 years ago in London Pancras Station. And what you see is depot charging of battery-driven electric vehicles. So yes, we've been there, but we got better technology now, and hopefully we make a breakthrough to reduce emissions in the transportation sector. So how does depot charging and batteries on bidirectional hardware work? Well, you got the grid, you got the power module to charge the vehicle, you got AC to DC conversion, but you got a stationary battery in between. And stationary batteries are nice because they can be built on cheaper material than the ones with a high energy density used in the vehicle itself. So the DC-DC converter, as well as the AC-DC converter, needs to be constructed to form bidirectional operation. The stationary battery can easily be used to shave up peak loads. You can charge the battery at low energy demand time. Particularly in Europe, there's for quite some period the day, the price for energy is negative because there's excess energy. Actually, you could arrange for being paid for charging the battery and not paying for the energy. Very interesting business case in the future coming up. So aligning charging times and energy cost will become a business of fleet operation inherently. Once the battery is charged, and the vehicles are too, you can offer grid services, balancing, frequency stabilization. That all comes with depot charging and is a very nice opportunity for fleet operators to offer a little service to the grid support. And supporting this also allows integration of highly decentralized renewable energies. There are depots constructed these days that are looking like halls, and the roof of the hall carries solar power. So with your own power source and your own power storage, it makes you independent from the grid, and it offers a great variety of services to the grid as well. Second option to charge is the so-called opportunity charging. Charge whenever possible and charge a lower amount of energy, typically by vehicles with a pantograph, and particularly buses in urban transportation are a good situation here. Charging by pantograph is done on a higher power level than charging on a depot. Simply because you have lower time, you need higher power levels. Starting at something like 125 kilowatt, but there have been systems introduced that can charge from 200 or even 500 kilowatt. A single vehicle is charged at a time, and the benefit is that charging for a few minutes during shifts can refill a small amount of energy, but some of those stations may be at the beginning of the line, the middle of the line, and the end of the line, where the driver changes, the driver takes a break, or there's longer periods for recharging. So here again, some side notes. Stationary batteries will be used in this case anyway. Typically in cities, you cannot easily get 125 or higher kilowatt rating from the local supply. So buffering this offers the same opportunities. So here too, the batteries can be used for peak shaving and aligning the batteries with aligning charging with energy prices might really help. And again, excess energy sometimes is available at negative rates. So this may do a lot for total cost of ownership in operating fleets. And if you think that this is brilliantly new just because the picture was taken on a recent conference, well, think again. Here's proof from Düsseldorf, a town in Germany, where in the late 70s to late 80s, a fleet of buses has been operated this way. And again, yes, technologically wise, we've been there. But today's batteries don't need to be towed in a tender. Well, it would be battery swappable. Actually, it was. But yeah, the battery technology has evolved. Power electronics has evolved. Vehicle technology has evolved. So hopefully the change becomes permanent. A third scenario to be talked about is the so-called wireless power transfer. You have a receiving coil in the vehicle to pick up the energy, a sending coil in the pavement or in the grounds to provide the energy, and the wireless power transfer talked about today targets a power regime less than 25 kilowatt, which makes it a little less interesting for high power vehicle charging because the charging power is pretty low. Charges one vehicle at a time, and the same is true as for buses. So in a short break, a little energy can be transferred. If this is installed on parking lots for the driver to take a nighttime, well, might be an option. However, very importantly, positioning matters. So proper aligning between the vehicle's coil and the ground coil becomes a necessity, which makes it a very nice addition to autonomous vehicles, actually. Also, the impact on installing it underground has a huge cost penalty for the installation. Opening up streets easily makes a project twice as expensive as just putting a charger with a wire on the same spot. Importantly, foreign and live object detection needs to be done. You don't want, for example, a can in the magnetic stream because it will glow hot, and you don't want to kill your neighbor's cat. So foreign object detection becomes a mandatory thing to have. It may not be a good approach in logistics and long-haul transportation, but it may be very well suited for local transportation. Take the baggage trolleys on an airport. Start and stop positions are fixed. Airport isn't public space, so installing this bit by bit might be a good addition. So in material handling and baggage handling, also in factories' internal handling systems, wireless power transfer is a great thing to boost commercial vehicle operation. Wireless power transfer inherently comes with galvanic isolation. So let's take a look at displacing the galvanic isolation and shift it to a different point. That's possible with wireless power transfer. And the standards for battery charging today prefer solutions that have galvanic insulation. But they don't make it mandatory, and they don't tell you where to put the galvanic isolation. You may use wireless power transfer, but there's a more tempting solution. If we're talking about megawatts, we're not talking about taking it from the low voltage 400 volt systems. We're talking about a massive backbone connected to the medium voltage regime, 20 kilovolts or 30 kilovolts. So a megawatt transformer can be created to produce several outputs of 690 volts, for example. And each of those outputs can drive an AC to DC converter. Well aligned, each of those could provide something like the 1500 volts targeted for high power vehicle charging. And if each of those provides 750 amps, well, 4 of them would easily provide the 3 kiloamps that the standard mentions. Paralleling those for the DC may easily provide the megawatts to a single vehicle. The transformer efficiency of a medium voltage transformer is unprecedented. They all run 99 point something percent, even 99.9 have been proven. And the insulation in the transformer is meant to support 100 kilovolts. So yes, the battery is separated from the grid with a galvanic insulation. Standard, fulfilled. It reduces material consumption because now the AC to DC converters no longer feature insulation on their own, which in turn increases the power density of the power electronic section. It would also allow for a redundancy operation if properly connected. However, this may not be the most reasonable solution at all. There may be something else that comes to mind. And by looking at different industries, there are similarities in charging. Charging a battery is very similar to doing electrolysis. You have a DC application and you want a precisely controlled DC current flowing through cells. Whether it's electrolysis cells that operate at 1 or 2 volts, or battery cells that operate 2 to 5 volts, depending on the chemistry in use, from power electronic view, it's the same application. So why not use the same topology? Use a specially created medium voltage transformer and use a B12C topology, thyristor based, and instead of electrolysis, well, power your batteries. It's the identical application, it's the identical control. The question is how many cells you need to put in series to get to the voltage level you target. And this is a single stage energy conversion application. In turn, it's the most efficient one you can build. So if you build this on a very classical thyristor, like this one, pick by choice, that's a 2000 volt thyristor. And at 1000 amps, you end up with about 2000 watts of losses per bridge. In turn, this means the conversion efficiency of this power stage is 99.8%. And that's an amazing number. How can thyristors be so efficient? This thyristor has a forward, is used in this B6 technology or topology and copied twice to form B12. If you take a look at the schematic and the data sheet, you'll find that the forward voltage of this thyristor on 500 amps is about 1 volt. So we're talking about, well, 0.5 milliohm resistance. That's pretty good. At 1000 amps, the forward voltage, because of the nonlinear behavior, only increases to 1148 millivolts. Rough estimation. RMS currents at this voltage, the losses sum up to 2212 watt, as stated before. Twice in all the bridges, it is 4400 watts, and the overall efficiency is 99.8%. That's a rough estimation because it only considers the RMS current. So what's the real value? And here's the result. Backed up by a Plex simulation, this is the losses in a single thyristor. And the single thyristor, according to this simulation, burns about 384 watt. So per bridge, my estimation, my guesstimate was just off by less than 5%. So 2,306 watts. As said, silicon carbide solutions have been reported to achieve 97%, potentially 98% efficiency. And that is because you have at least a two-stage energy conversion if you don't have insulation. With an insulated version, there's three stages of conversion, and each stage is burdened with losses. Single stage energy conversion can achieve 99.8% efficiency. And that's not all of it. There's more, and that is the resources per kilowatt installed. So size matters, and everybody today is looking for solutions that need a lower amount of resources to do the same thing. Actually, the slogan is do more using less. So here is a stack to form those B12 technology. And you can see that it's roughly a meter in width, it's 90 centimeters in height, and 75 centimeters in depth. So how does this compare to a typical solution using MOSFETs and thermal management for the MOSFETs? And here is a schematic or a scheme drawn to the scale. So if you achieve 97% efficiency on a solution and you're handling megawatt, you need to get away a lot of power. So the losses in this gray blocks stack up to 60 kilowatt. And the combination of chiller and radiator to handle this sort of heat and really make the thermal management for the power electronics turns out to be quite big. And as said, we're talking about units 60 to 70 or 100 kilowatt. And if you try paralleling those, you would need 42 units to fulfill the 2.2 megawatt solution. But you only need this one stack consisting of two B6C topologies. And the efficiency is so high that you get away with forced air cooling. So the infrastructure is getting far less complex if you don't need to have your power electronic liquid cooled. Or on the other way, if you use liquid cooling, you could get even more efficient with even smaller components. Small is a good buzzword. The classic approach would lead to something almost 6 cubic meters in size for a single charging entity, while the power section only has 0.6 cubic meters if you choose a thyristor-based solution. So thyristors may seem ancient technology to a lot of young students and people who haven't worked with them, but I think they deserve a second look, particularly if it comes to megawatt application. As I'm convinced it is so, look out for this year's PCIM. There is a paper that is titled The Resurrection of GTOs and Thyristors as Components in Megawatt Chargers, as well as in railway and mining refurbishment. So this is a topic that's going to be part of the presentation at PCIM 2022. Also in the matter of scope is the last mile delivery, particularly the low-speed vehicle. So two-wheelers for transport in city, three-wheelers for transporting goods and people, and also four-wheelers in on-road and off-road transportation turn to be electrified, and they're electrified in huge quantities. This means we see millions of rickshaws being built annually, and more passenger transportation systems like this switch from two-stroke or four-stroke engines to electrification. Passengers and goods are transported, and particularly in rickshaws, it's almost balanced. 56% are used for passenger transport, 44% are used to transport goods. And rickshaws are very popular, particularly in the monopoles of this world. So it's not only New Delhi or Bangalore, it's also cities in South Africa, South America, and Asia that have rickshaws as a transportation system. Trouble is that they're not included in the automotive standards or industrial standards, and in some countries, rickshaws are considered motorcycles. So, difficult to find a proper standard to refer to, but very common. They all run in low voltage, in something like 48 to 96 volt, and this is all below CCS standard. So, which standard to apply for charging is uncertain, particularly because there are a lot of concepts used. So battery swapping became popular, for example, for scooters. onboard chargers have become popular to plug those vehicles into any outlet available, but also higher power offboard chargers are installed, up to 10, potentially even 15 kilowatt, simply to support those last mile deliveries vehicles wherever possible. And the good thing is, they don't need a dedicated infrastructure because 8 or 10 kilowatts typically are available literally anywhere where there's electricity. So in contrast to the high power vehicle, to the heavy duty commercial vehicle, how does the scaled down version look like? What about the last mile delivery or the low speed EV? Well, it too has a battery that demands proper battery management systems. So again, it's pressure sensors, temperature sensors, and low voltage MOSFETs required. Even if it's not 1,000 volts, anything in a vehicle exceeding 30 volt is considered high voltage and needs an emergency disconnect. Same is true for the low voltage part. There's for sure onboard electronics like lighting, convenience electronics, and window wipers that deserve control by low voltage MOSFETs and the according gate drivers. There may be electric fuses in use because they become very common in vehicles as well, and more advanced diagnostic comes along. And mostly, but not exclusively, discrete MOSFETs and diodes are used in DC-DC converters. And the same is true for the onboard powertrain. So here, the inverter typically is built using discrete MOSFETs. However, there are small power modules that could be used as well. So it doesn't look like a big difference in structure, whether it's a small vehicle or a big vehicle. So how to do a comparison about the drivetrain? What about the heavy-duty monster compared to the three-wheeler? They both need a battery for energy storage. They both feature DC to AC conversion to drive the motor. They both feature DC-DC converters to drive the onboard low-voltage systems. So on block diagram level, there's not that big of a difference. The difference is that the DC to AC converter in the heavy-duty vehicle will be burdened with up to 1500 volt DC, and 150 or 250 kilowatt per inverter are easily seen. While the input for the low-speed vehicle is below 100 volt, and typically we're talking about single-digit kilowatts, maybe 10 kilowatts at the top. Same is for the DC-DC conversion. Here too, the battery voltage is far higher for the heavy-duty vehicle, and the output may be 12, 24, or 48 volt. There are trends to go for slightly higher voltages than 12 and 24 volts to reduce the current to achieve the same output power. And 24 and 48 volts became common in trucks and buses. The input to the low-speed vehicle is 48 to 96 volts. But the output is typically 12 volts. They don't deal with 24 volts, and the output power needed typically doesn't exceed a kilowatt. So here, the components and the designs get smaller, but the setup inside may be very similar. The line to be drawn between those systems is that the left part in the high power regime typically is based on power electronic components 1200 volts or higher, while the low-speed vehicle typically ends up with MOSFETs being used lower than 200 volts. But as said, the whole thing may change in size, and size matters, but the good thing in power electronic is it's scalable. So if your vehicle looks like this and deserves hundreds of kilowatts, it has a six-pack typically driving a permanent magnet synchronous machine from a large-scale battery. Very prominent in this design is having half bridges in a single power module, and those modules are easily available in 1200 and 1700 volts, easily up to 600 amps. In comparison to that, on a low-speed vehicle, you have a six-pack of MOSFETs driving a brushless DC machine. And brushless DC is the synonym for permanent magnet synchronous machine. The battery gets smaller in capacity, but the schematic is very similar. And all of this could be built into a single module. So the Isobus module is available in MOSFETs from 55 to 150 volts. And depending on the voltage class, currents go up to 200 amps. Other products in the Isobus family, and I refer to the Isobus because of the convenience in thermal management, include discrete packages like the TO220 or TO247, easily make your same six-pack available. So that's for the drivetrain. How about scaling chargers? Well, there was a chat about this charging opportunity to do something like 10 kilowatts to potentially 100 kilowatts, which isn't needed in that regime for the low-speed EVs. But changing it from three-phase to single-phase to have it with a plug that's almost omnipresent and everywhere available, the schematic doesn't really change this much. So the input rectifier, in this case, is a PFC stage. And then there's an LLC stage driven by MOSFETs, rectified by diodes, and giving an output anywhere between 48 and 200 volts, particularly to serve the range below the CCS standard. And being driven from a single phase, the output power tops out at something like 3 kilowatts. So with all that said, where is the little fuse contribution to this? In the electric vehicle, the fuel cell vehicle, agricultural vehicle, material handling, charging, energy storage, energy generation, low-speed vehicles, and the according infrastructure, and of course in passenger cars as well. Little fuse can help you easily to handle megawatt solutions in energy generation, getting down to hundreds of kilowatt solutions in all the applications talked about, down to single-digit kilowatts, which literally means we got solutions to offer to help you in 12 decades. From milliwatts to megawatts, we can find a solution on your power semiconductor needs. As a remark, we talked a lot about little fuse delivering answers to your semiconductor needs. So yes, there is power semiconductors, but there's dedicated solutions for EV charging. There is high voltage relays and electricity add-ons for electrifying commercial vehicles. We have quite a footprint in mining equipment, and the topic spent or not talked about today was fuses, and particularly in the high voltage disconnect, where fuses are a mandatory thing. Little Fuse has quite a portfolio to protect your precious battery and semiconductor inside your electric vehicle. So with this, we finally reached the point to answer your questions. Before we do so, thanks for spending the time with Mother and Little Fuse on this webinar. Thanks for being with me on this webinar, and I hope you enjoyed the session. So we now open up the chat and ask the moderation, are there any questions we can help with?
Yeah, thank you so much, Dr. Martin. And just to share, so a few questions came in about, will the presentation be shared? Yes, something will be sent across to you, but later on, okay? Right now, let's focus on, we have a brilliant resource like Dr. Martin live with us. So let us utilize and leverage that presence. Dr. Martin, a few DMs and messages that came to us. Can you tell us a little bit more about the Indian perspective, if any, that you're having? You must be talking to a lot of people. India is on a tear. We have to improve urban mobility. And, everyone is waiting for a massive shock that is going to come in because of petrol and diesel fuel prices are going to go up. So keeping that in mind, is there some perspective or inputs that you'd have, Dr. Martin?
Yeah, for sure. So particularly the rise in energy costs these days, particularly in fossil fuel, and the climate change and the restrictions and governmental impacts on having lower emissions makes the transportation sector a primary target for electrification. Throughout the world, as a rough rule of thumb, only 25% of the vehicles are, only 10% of the vehicles are commercial vehicles, but they consume 25% of the fuel we spend in transportation. So electrification is a big deal. And you see that there is corporations like Bharat-Benz or Tata, where India has its own production of heavy-duty vehicles. So here, I know that both those companies are already into electrification. And my personal feeling is that battery electric vehicles will make the race. I'm not convinced that fuel cell vehicles will win the race or make the race, because today's hydrogen is taken from oil and gas, and generating green hydrogen is very energy intense. So from efficiency point of view, the battery will always outperform the hydrogen solution. And in logistics, the cost for energy really matters. So there's an option to go green with hydrogen, but there's no option to go cheaper with hydrogen than you could do with batteries. So I do see that the Indian market can easily grow into becoming a large opportunity for electrification, starting from the drivetrain, going down to convenience system, and starting from heavy-duty vehicles in 40 tons and above, but also going down to the last mile delivery and in-city delivery. You see that rickshaws are so prominent in India, and recently the two-stroke engines have been banned and needed to be replaced by four strokes for efficiency and air quality reasons. Some companies have changed to CNG recently, which is even better, but the big thing will be electrification. And there are companies out there that already have a nice fleet of electrified vehicles in that class in the field. But I see that there's a lot of space, particularly for innovative startups to join that market.
Yes, thank you. There is one question, if you see that on the chat as well. I'm assuming it's that for heavy duty, would it make sense to have battery swapping? That question has come in on the chat. Would you like to put some light on that, sir?
Yes. Battery swapping looks nice on paper and has been tried a lot of times. But coincidentally, all the battery swapping projects have died. So Project Better Place, gone. A project in China where battery swapping was installed for urban buses, didn't make it. One of the big issues with battery swapping is the contactors. We're talking about vehicles that consume thousands of amps on acceleration. So the contactors have to carry kiloamps. And you have a DC source that goes up to 1,000 volts. So having this replaced over and over again is an issue. But the bigger issue I see, and that is historically proven, is that the vehicle manufacturers not easily give away their design freedom. So battery swapping would first demand standardized batteries. And that is something where the manufacturers never agreed on a common form factor. And I don't see that every company has its own battery, its own vehicle, and its own swapping station. That is what, for example, NIO is currently doing in China and also trying to export it to Europe. And though it's really looking good on paper and really looking good on swapping times, I'm not sure whether this will make a big impact. For a single fleet operator in a single entity, maybe yes. But there's so many issues with swapping batteries, legal-wise, owner-wise. I don't see really how this will make it to a mass market. To a local market, maybe yes. To a mass market, I don't see that.
Okay, Doctor, thank you so much, Dr. Martin. Dr. Martin, one question that we would love to ask you is that you are talking to audiences and people right across so many countries. So keeping that in mind, how exactly do you see policy making a difference in this industry? If you have
the policy is the difference, actually. So a lot of states, for example, take California. They always had the most restrictive economic rules in the US, and they have simply banned diesel-driven transportation in 2025. So whatever company is selling trucks and buses in California in 2025, if they don't comply with the zero emission mandate, they have to expect huge penalties. And that is why they're driven to create zero emission vehicles and operate zero emission vehicles in California. But it's not only California. There is the C30, the biggest 30 cities around the world. And by now, they all filed similar policies. So whoever wants to operate a fleet and to build vehicles to operate fleets has to comply with zero emission. How they manage? The policy doesn't matter. But battery electric vehicles, I think, are the most promising way to get there. So yes, it's policy driven. And of course, people get more and more skeptic about climate, about air pollution, about quality of air. And having electrified vehicles around instead of diesel or gasoline driven ones, air quality dramatically increases. And if you take a look at the smog in all the big cities, be it Moscow, New York, Paris, New Delhi, Bangalore, name it. They all got smog issues. They all got lung cancer issues, and they would all benefit from having lower pollution rates. And as said, transportation is responsible for 25% of the fuel used, literally for 25% of the pollution coming from traffic. So policies tend to get rid of that.
Thank you. Thank you so much, Dr. Martin. There is a question that has come in, and I'm sure you'll be able to give us some kind of input in terms of the optimum time that for a full charge for a commercial vehicle battery.
Oh, tricky. We're on the edge of converting combustion fleets into electric fleets. In parallel, we're on the edge of converting driven vehicles to autonomous vehicles. So from today's point of view, whatever is fast enough to recharge the vehicle 80% during a driver's lunch break is perfectly fine. Consider that a larger truck will carry something like 400 to 600 kilowatt hours. That is 80% of that. We're talking about 500 kilowatt hours in half an hour. 500 kilowatt charging would do fine. You want to be faster? The standard today allows 2 megawatts. So having 500 kilowatts refilled in 15 minutes. If your vehicle starts to be an autonomous vehicle, then there's no need for a driver for a recreational break. You want your vehicle to be recharged in the smallest possible time. And the high power charging standard is open to be extended to 4.5 megawatts, which means 500 kilowatt refilled in 7 minutes. And that is where development is going towards already. But let's do a step at a time. Get the 1 and 2 megawatt chargers up and running on the infrastructure. And then I think in a second wave, starting something like before 2030, we'll see chargers with even exceeding the 2 megawatts being built and set up.
Thank you. Thank you very much, Dr. Martin, for this very finely articulated answer. So one of the other questions that we have got in our various groups and forums is coming in is that while you're operating across many countries, you have a partnership, you're working closely with Mouse Electronics. How does innovation, academia, and young startups, what can they look forward to and what should they be focusing on? Where do you see gaps which they can work on? If you could throw some light on that, please. Thank you.
Well, you saw the value chain. Pick any of the puzzle pieces of your preference, be it the vehicle, be it the charger, be it energy conversion, be it renewable energies. There's a huge demand for engineers in all those disciplines. So whether it's the next best renewable energy system, we're talking about solar and wind power a lot today. There is tidal wave power generation on the verge. A lot of thinking and a lot of research is going into energy storage. Doesn't necessarily need to be battery energy storage. Could be high-speed storing by flywheel. Could be larger amounts of energy currently developed as undersea pressure storage. So we need a lot of innovative ideas how to store energy. A lot of talk is in the media about a lack of energy. Let's put this very straight. The one thing we have in excess is energy. The thing we don't have is a decoupling of energy generation and energy consumption times. And the missing link in between is energy storage. So we need to do a lot on energy storage. We're currently setting a lot of money on lithium-ion technology for batteries, and that's good because the lithium-ion battery has huge potential. And I see that the energy density for batteries will grow by a factor of 5 in less than the next decade. But it's a lot of material insight. And the question is whether there is development of the next better battery technologies. A lot of research is going into this, partially on material science, partially on chemical industry, partially on packaging industry. So there's something like 100 PhD students that I can support with topics from tomorrow easily. So lots of space for research and a lot of space for startups.
Thank you. I'm sure that's music to the ears to all the innovative startups and the founders who are here. Thank you so much for that, Dr. Martin. All right, there's one more question that is coming from Yu Yang, which you'll see on the chat as well. This is around bi-directional charging of the battery. What will be the industry standard which is necessary for grid modulation? Will bi-directional charging by the industry be the industry standard which is necessary for grid modulation? That's a question that's coming.
Not sure whether I get the question right. If you want to know a standard for vehicle to grid, I'm sorry, I can't get you an IEC number or an EN number or whatever JDEC number for this. But generally, vehicle to grid is something that will happen or already happens right now. One of the prominent examples is the Hyundai Ioniq 5, which already has vehicle to load capability. And it's a very small step from vehicle to load to vehicle to grid, or vehicle to home, vehicle to vehicle. So as said in my example, if you have bidirectional chargers in a fleet operation, the question is, what is making your bigger business? Transporting people twice a day or offering energy services? And if you pay for the precious good in your vehicle, the battery, you don't want to be a sitting duck doing nothing. So earning an additional money on using the battery for grid services is a great thing. It's so good that even in my house, I use a battery to support my solar array. And that's a bidirectional battery as well. To my regret, it's not my car, but generally, the car's battery could play the same trick. And that is something that I see coming in the very near future, so that decentralizing energy storage and energy generation and energy consumption really makes a relief to the grids. And the grids are burdened already to the max in a lot of countries. Some countries, and India isn't an exception, have quite a weak grid where power outages and brownouts are more a frequent thing than the exception. This could dramatically be reduced by having stationary batteries supporting this grid. And stationary doesn't mean it's immobile. Stationary means it's located in your vicinity. Maybe it's parked in your garage.
Interesting, Dr. Martin. I'm also giving a quick shout out to Soma, if you'd like to come in. He's from FinExcel. And we have our wonderful partners. We have Saswati, Avinash, Suman here as well. And we also have Vinay Dora. Vinay, if I missed out any questions or anything has come to any of our other groups, just let me know. And the other thing, Martin, is that if you have to look at, say, crystal gazing 1 year or 2 years ahead, okay, what would you say would be there? And before that, I would like to ask you this one more, which is coming from Avinash, that we would like to understand the lifetime of EV battery, and what does this do for EV technology and standardization?
Mm-hmm. So yeah, that's one of the big concerns always. If you talk about electric vehicles, people easily conclude, well, the battery won't last that long. But recently, battery vehicles have been driven for, I think there's one Tesla Model S that achieved 1 million miles. And that's a small battery in a passenger car compared to a heavy-duty vehicle. So if there is an option, or there is a lot of development in batteries, and it's always about the ratio of load to the battery and battery capacity. So it's one thing to take 100 kilowatt from a 20 kilowatt hour battery. It's a totally different thing to take 200 kilowatt from a 600 kilowatt hour battery. So the stress for a large battery in a large vehicle is lower than in a passenger car. And that's why my prediction is, if there's battery technology today that can last 1 million miles in a passenger car, it's clear foreseeable that there is the same or even better technology in a less stressful operation to last more than 1 million miles. And that's the deal for the heavy duty vehicles, the 1 million mile limit. If it survives that, it's fine. And then again, the battery itself is a costly part of equipment in the vehicle. The question is, what's the total cost of ownership, assuming you have to replace the battery in 10 years? In 10 years, the battery you buy today, or the battery you buy, will be much cheaper than the same capacity you buy today. So the lifetime of the vehicle, the service time, maybe 10 or 15 years with the first battery, but it may easily be another 10 or 15 years with the second battery. And there have been projects started in New York with buses that turned out that an electric bus towards a combustion engine bus saves about $1 per mile. So driving 1,000,000 miles easily, you save $1 million. So if the vehicle is $100,000 additional dollars because the electric vehicle is more expensive, and after 10 years you have to spend $1 million on or $500,000, no, not $500,000, but let's assume $250,000 on a new battery. Well, then you spend an additional $300,000 or $400,000, but you saved $1 million in the same time frame. So I do see that the electric vehicle is the more reliable and more robust vehicle. You don't have all the heat generation entities inside that accelerate aging. You have a lower number of moving parts. I think that from the perspective of total cost of ownership, that's also a very good start, because an electric vehicle can be refurbished with a better technology in a few years. But you would not take a 1920 Porsche and put in a 2000 motor just because the motor is 5% more efficient. But I foresee that you will maybe take a 2022 truck and refurbish it in 2035 with a brand new set of technology, because the mechanics don't wear that much. It's the engine that wears in combustion engine, and that's gone. So giving an example, my own passenger car, electric, built 1995, came with lead gel batteries. When I bought it in 2007, a lithium-ion battery with the same capacity would have been almost 20,000 euros. In 2014, I replaced the battery for only 7,000 euros. The lead gel battery is still cheaper, it's 4,000 euros. But the lifetime of the lead gel battery is something like 50,000 kilometers, while the lifetime of the lithium-ion battery is 500,000 kilometers. So yes, replacing the battery is more expensive than using the old technology, but from lifetime perspective, total cost of ownership, it's a great deal replacing it with a new technology. And the same will happen on industrial level, on commercial level. And I foresee that trucks can easily be refurbished with better technology in future, which is an option you don't get from combustion engines.
Thank you. Thank you so much, Dr. Martin. And this is a comment that has come in about how interesting and informative, and you have shared this information in a very interesting manner. So thank you so much for that, Dr. Martin. Great. It's 5:05, so we want to just be a little bit careful on time. But crystal gazing, as you're saying, the future trends. So then we'll not ask you for a 10-year thing, but at least say over the next 2 years or 3 years or maybe even 5 years, how do you see the various trends in terms of cost and weight and adoption of new technologies? Anything that you're seeing across the world?
Yeah, very clearly, we're starting an age of electrification, and this will make a holistic approach highly necessary. So it's not only getting the vehicles onto the road, it's also getting the green power into those vehicles. So the trends, for example, in the European Union are very clear. We have to increase the content on renewable energy in the grid and in the supplies. That's one trend. The tendency for electrification of vehicles of literally any kind, from motorcycle to heavy duty truck. Autonomous vehicles, I'm pretty sure that because of the cost for the driver, I assume that we'll get to see autonomous buses well before we see autonomous passenger cars. Anything in logistics that's money is the investment for the vehicle, the cost of energy and maintenance, and the driver. Energy consumption or cost for energy will be declined by electrification. The invest for the vehicle will grow. So the next thing to optimize is cost for the driver, and autonomous vehicles are the way to get there. That's why my prediction is that I see prototypes on the road within the next 5 years, and I see larger fleets being operated in the next 10 years. In the next 2 years, I think there will be a change in mindset with a lot of manufacturers that still believe that improving the efficiency of combustion engines is an option. A lot of OEMs for passenger cars have already stepped away from this opinion. And if you follow the media recently, a lot of manufacturers have set a deadline for the last combustion engine to be built. And I think the same is going to happen for commercial vehicles as well.
Excellent, Dr. Martin. Thank you so much.
Major trends for power electronics will be developing of more reliable and more compact assembly structures. Potentially, the footprint of wide bandgap materials may increase, but that's something I'm not totally convinced that silicon carbide is the better choice in commercial vehicles, particularly because of the lifetime aspect. So that's something to be reviewed carefully and considered. And very clear, the tendency for higher voltages is already set. So today, 920 volt is the maximum. The very near future, I think we're going to see first devices on exceeding 1,000 volts and approaching the 1,500 volt level.
Excellent. That's very comprehensive, and thank you so much. Avinash, Saswati, is there something that you'd like to step in and share? We'd be more than happy to hear from you. Or if there are any further inputs, please go ahead. Avinash, go ahead.
Yeah, we would just like to thank Dr. Martin and Little Fuse team for giving such a wonderful insight. And he did answer even my queries because I'm very much interested about the technology. So thank you, Dr. Martin.
My pleasure.
Thank you, Dr. Martin. And thank you so much for your time.
This has been really good, Dr. Martin. Is there anything else that we can do for you? How well do you know India? Is there something that you want to kind of get to know? I'm sure you're in touch with Avinash and Saswati, but if there is something.
I'm pretty sure that you're well interlinked with my colleague Navneet. And Navneet, also thanks for initiating this and taking it through. That's really appreciated. And yeah, it's always about the communication and flow of information. The better information we get, the more information we get, the better we can help. And help is what we really like.
I think a last word, Dr. Martin, you have covered the topic really, really well. You know, it was very engaging and it was very interesting for us to hear so much about it. Thank you.
It was my pleasure. Then, thanks for the opportunity. Thanks again to the audience for spending the time with Mauser and Little Fuse on this topic. And I hope we get more thrilling topics for you to present in the near future. This said,